Hello, I'm David. I'm the coordinator of the Maths Learning Centre here at the University of Adelaide. It's semester 1, 2025, and this is the revision seminar for data analytics. And now you've seen my face, I'm going to go to the document camera. Okay, so these are the requests I've had. And I would like to say to those here in the room that this seminar is for you. Please ask questions when they occur to you. Maybe wait till I finish a sentence, but otherwise that's okay. If I make a mistake, please interrupt me immediately. Don't wait for 5 minutes and then go, oh, back 2 pages ago, you put a minus somewhere where there should have been a plus. Don't tell me that. Don't wait, tell me immediately. And I will try my best to remember to stop every 5 minutes or so to check how you're doing. But it's totally okay to interrupt me if you've got a question, okay? Because this is your seminar, and it's all about helping you to make sense of what's in this course so that you can feel better. All right, we're going to start with some hypothesis testing. Okay, and we're going to need to have a bit of a brainstorm on what sorts of things have been in hypothesis tests. So you've mentioned T's and p-values and critical values. These are some things that you've mentioned so far. So I'm pretty sure that this course talks about rejection regions. Is that right? Yes. And obviously the phrase is reject and Can I ask if anyone remembers what the opposite of rejecting is? Retain? Fail to reject. Cool. This is one of the things that's different in different courses. Other courses call this retaining as opposed to rejecting. So if you Google random things online, you'll find that the terminology for not rejecting is different in different disciplines. So some people call it reject and accept, some people call it reject and retain, some people call it reject and fail to reject. So there we go. Just going to bring poor old document cameras. We bought them during COVID and haven't bought new ones since, and they're getting a little sad. Okay. All right. But we didn't want to buy new ones in case someone in the new university sprung for new ones for us. So, okay. So, cool. So these are all terminologies that go with all of the hypothesis testing. And any hypothesis test you do will tend to have all of these things in it. Any other terminologies that go with all of them? I guess null hypothesis, that'd be in there somewhere, wouldn't it? Okay. All right. So this is kind of like the common terminology to all of them, but then each situation that you're in based on the kind of question you're asking and the data you've got will dictate what kind of hypothesis test you do. So if you've got your situation So the situation you're in and the kind of data you've got and the kind of question that you're asking, all of them together tell you what type of tests you're going to do. And in the text of an exam question, sometimes one word will make all the difference to which type of test you choose to do, which is frustrating, but there you go. Okay, so what kinds of tests have you got? So brainstorm, there's no wrong answers. Well, I don't know. It's a collection of right answers. Oh, yeah. All right, and these go with lots of different kinds of tests as well, don't they? I think. Maybe. We'll see. But these are things that are possible, things that we have to choose between, and that will be based on the question that we're asking. Cool. The null hypothesis is also based on the question that we're asking as well. That makes a difference to that. Okay, so I'm going to give you an idea. I'm pretty sure that in this course, you have various t-tests because you'll have a test that you calculate a t-statistic in. It's usually called a t-test. And you'll have ones that are about a single mean and ones that are about two means and that sort of thing. Does that sound familiar? Do they get you to do a paired t-test in this course? Paired. Nope. Okay, cool. Worth checking. Yeah, P-A-I-R, paired. Nope, all good. Useful to know. It's really common in the other courses, so I just wanted to check. And I'm almost certain in this course that the two means one comes in pooled and unpooled versions, yeah? Oh, cool. And then all of these come in tailedness, right? So they all have left and right and two-tailed versions. Okay, good, good, good. Just checking. And then I guess there's probably some Z tests too. Now, did you do a Z test that went with a mean originally? Yes, you did. You did. I know this because it was in the first or second assignment. And that went with a single mean as well. And did you do any hypothesis tests that go with proportions? Like where you had like a p hat and a p and that sort of thing? Or did it only do confidence intervals in that setting? Okay. But there was things with, okay, no hypothesis testing there, but confidence intervals maybe. You'd have to look it up and I'm happy to wait while you do. Okay. It would have a whole week of its own on proportions probably in my uni. Don't want to miss anything. Standard you use the same for the okay, so yes, you did found and the report is beautiful. Just a screenshot I took of my notes. Notes if you want. That's one of those things that I need to look at, but it's not always pretty. Okay. If you find it, if you open my uni and find it, then let me know. But at the moment, it looks like we're just going to talk about this, and all of your hypothesis tests are about means so far. Is that true? Okay, cool. Those watching this video in the future, and any of you guys, if that's not true, I apologize, but this is what we're working with at the moment. But feel free to come to the Maths Learning Centre if it turns out there's more of them, and we'll chat about it at the time. Okay, so that's good. That's good. Just give me a second. Has anyone got my uni open? Can someone open my uni? I just want to have a look. I just want to be sure. I mean, the My Uni for this course is frustrating because there's 10,000 clicks to get anywhere, but and you never know what page the thing you're looking for is going to be on. This is where I would like there to be a textbook as well that was just scrollable and searchable. It's My Uni frustrating. And multifactorial authentication. Yes. Okay. 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 Cool. Yeah. That just cuts down the hypothesis test by half from what it used to be. It's not awesome. Sorry? No. Yeah. About before they rewrote this course, there were like 12, I think, when you added them all up. I mean, already you've got 1, 2, 3, 4. Yeah, there's 5, 6, 7. Well, anyway, times 3, 12, I suppose. But anyway, excellent. We'll leave it like that. That is very pleasant from my point of view, comparing to the other statistics courses. The one that the science students do has 15 or something. So, okay. Cool, I'm going to number this page so that I don't lose track later. Okay. So, I find it really useful to think about the situations that these things happen in, and all of your hypothesis tests are about the value of a mean in this course. And so your question, or possibly two means, depending on whether, well, there's various bits and pieces that help you decide which one is which. So let me see if I can remember it and we'll get it right. So in this course, all tests concern means, which means that the research question or the question in the person's mind in the exam question will be about a mean of some sort. And it will be about whether a mean is more or less or the same as a specific number, or whether the mean is more or less, the mean in one situation is the same as the mean in another situation. So they are the situations. And so there's your courses split them into the one mean and the two means in separate weeks. And that's not the worst plan. So I will have some water. Okay. I'm just going to step back a bit. One of the reasons I spend all this time on sampling distributions in this course is because that theory of sampling distributions is what hypothesis testing is built on. And so when hypothesis tests were invented in about the 1920s, actually this year's the 100th anniversary of the p-value. It was first published in 1925. So there you go. So first used for agriculture. All right, everyone gets my notifications. That's fine. So all the tests concern means, and they are based on a concept of sampling distributions. But ultimately, they have to have distributions in them because we're going to calculate a probability, which is what a p-value is. And all probabilities are a comparison to what has happened or what you're thinking about to all the things that could have happened. And that is what probability and therefore a p-value is. And so the idea is that you are imagining all of the sample means that could have happened in all of the samples that could have been taken. And that is what you do in a hypothesis test. So you imagine So you imagine all the samples that could have been taken and all the sample means that could have been calculated. Compare your sample means to them. And when you do that comparison, the likelihood of getting a sample mean like yours or worse is the p-value. But that is what you're not doing any of these things really, but that's what's really happening in the background. You're imagining all the things that could have been and comparing what you've got to them. And modern statistics, which is not what you're learning now, often does that by literally running simulations in a computer and comparing them. But what you're doing is something that could be done by hand 100 years ago without a computer. So, though it is still quicker with a computer now. So you do that, and then you get a test, and then you get a p-value. But it's much harder to do it directly on the means, and what you do is you do a calculation based on the means and the standard deviations to get a test statistic. And some statisticians have done some careful calculations of all of the test statistics that could have been so that you can calculate the probabilities. Yeah. So what you actually do is calculate the test statistic and imagine all the test statistics that could have been and compare yours to that. So this thing of all the test statistics that could have been, that's called the distribution of the test statistic. So this thing, all the test statistics that could have been, that's the distribution of the test statistic. That's what that is. And so in your course, your test statistics come in two flavors. They come in Zs and they come in Ts. And the Zs happen when you suppose that you know the true standard deviation of your original data, of the original population that the data came from, and the Ts happen when you don't. So your first thing you need to know is that, do you know the true standard deviation? Welcome. Do you know the true standard deviation of the population? Yes, I know, or at least I assume. Then you're going to use a Z. And no, I have to get it from the data. and then you use a t. That's the difference between z's and t's in this situation. I'm going to stop at this point and say, does anyone want to ask or say anything?
I was just going to double check. You can also use the statistic when sample size.
Oh yeah, you can use the z statistic when the sample size is really big, but that's only because when when the sample size is really big, t is the same as z. Sorry. Yeah. So or over what's presented in the table, basically. So if your table goes up to 1,000, then that's when you switch to Z. But yeah. The table that you sent me, just let me, the table that I got sent gets to Z at after 200. Yeah. So if you look here at this degrees of freedom, that's based on the sample size. It's getting higher and higher and higher. And then at this point it says infinity. That's the Z. So, but once you get over 30, look at these numbers, these T's. It's 2.86, 2.87, 2.87, 2.86, 2.8. Like they don't change very much when you switch from look at this, it's 2.88 from 130 to 200. It only changes by like this third decimal place, the T statistic. And so at some point you can just go, oh well, stuff it. It's not going to be that different overall. So that 30 mark, if your lecturer says 30 is the go, then go for it. But other lecturers say other things elsewhere in the world and elsewhere in the uni. So just check with what your lecturers said. Yeah. My instinct is that if you've got the table, if you will do it as far as the table goes. And after that, then you use Z. But that's my opinion. Okay. All right. But that's the main idea. And one of the useful, but we're going to step back a bit. The Z distribution, there's only one. It's exactly what it is. Looks like this. Approximately. And these are all the Zs that could have been, and this height is how likely they all are. Oh, crap. That's because I'm still sharing the... This is what the Z distribution looks like. These are all the Zs that could have been, and this height is how likely they are. So it's much more likely for a Z to be near 0 than it is to be near anything else. And once you get it past here, it's very unlikely. And the actual probabilities are areas. So these heights aren't probabilities. The heights are, well, I think the official word for it is likelihood, but you can only really tell the probability of being in a particular zone rather than a particular number itself. So it's the chances of being between here and here is this area. That's how probability distribution diagrams work. And your Z table, I'm just going to check just to be sure. That's the T table. Your Z table, yep, shows the probability of being less than where you are so far. So in the Z table, it only shows probabilities like this. Everything from here that way. And that's the only thing it shows. So if you need a probability on the other side, you're going to have to do 1 minus the thing that the table shows you, because the total is 1. Anyway, that's how the Z works. And the T's, on the other hand, there's a whole string of different T's, one for each degrees of freedom. And that degrees of freedom is based on how much data you've got. And it'll be different depending on the situation you're in, how you calculate the degrees of freedom. So the T's, there's one like this, and then they get shallower and shallower until eventually they end up looking exactly like the Z. It's usually not that obvious to the naked eye. Most people, when you draw a T distribution, it's very, like if you draw it in a computer, it's very hard to tell the difference between a Z distribution, but the probabilities do turn out to be just a little different. So, yeah. And so you'll get degrees of freedom is 1, and degrees of freedom is 2, and degrees of freedom is 3, and blah, 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 blah. And then if you go all the way down to the degrees of freedom is infinity, now that's the Z distribution. So there you go. That's how the T works. But it works the same as the Z in that the most likely thing to happen is to get, most likely number to be near is 0. Yeah, it's just the lower the lower degrees of freedom, it's more likely to be near the middle than it is. No, crap, it's the other way around. I was wrong. They get taller, actually. Sorry. There we go. That's better. They get taller as the degrees of freedom goes up, and you get it more likely to be near the middle than it is near the edge. Yeah. Yeah. And when Gossett invented it, it was pretty cool. This was invented in the Guinness beer factory for use in quality control. So we're getting closer to economics there. Yeah, so, and he couldn't publish under his own name because all his research belonged to Guinness, so he published under a false name, which was student, which is why some people call it the student's t-test, or the student's t-distribution. There you go, there's a little bit of history. I think that was actually before p-values were invented, but anyway. Gossett won an award for the t-distribution, and he said when he won it, that's all right, someone else would have discovered it anyway. He was very, very humble, was Gossett. I think we should all be more like him, actually. He was a very nice guy. Fisher, who invented p-values, was not a nice guy. But anyway, he was a racist. He was a very smug gentleman, was Fisher. Refused to explain anything that he thought was obvious. But Gossett, on the other hand, was like, oh, yeah, this is fine. I'll explain it. If someone else would have discovered it if I didn't. Yeah, that's my philosophy of statistics. It's much better. Okay, so that's the big first question you have is, do you know the real standard deviation of the population, or can you just assume what it is? And if you do, then you can use a Z statistic, and otherwise you need to use a T statistic. And in real life, you don't know the true standard deviation of the population. That's not something that most people know. And so in real life, mostly people use T. And in real life, that 30 cutoff for using Z, people don't do that because the computer can totally calculate a T distribution for any number and they just let it do it. Because they get the computer to do it for them. So no one worries about that anymore. But 100 years ago, when p-values were invented, yeah, it was a huge and important thing to not have to look up the t-table. Made things much faster. So if you're in an exam where you can't use a computer, then it makes a difference then too. Okay, so then the other one is, a big question you have is whether you're comparing two populations or two situations or not. And that will make a difference to the kind of calculation you do. And I'm just going to list them all at the moment. So we have a Z test for one mean. And the question is usually, is the mean this number? So for example, something like, is the mean sales for a week $5,000, for example? That's a classic one. Or is the mean volume in an ice cream tub 1 litre? Those sorts of questions. And both the z-test and the t-test for one mean go with those sorts of questions. And so the z-test for a mean, and the t-test for a mean both do the same calculation to calculate the test statistic, but in this one you calculate the mean from the sample minus the mean from the hypothesis. Did they just put mu here or a mu 0? Okay. Divided by the standard deviation of the population. And this one is the mean from the sample minus the mean from the hypothesis divided by the sample standard deviation on root n. Like that. And this is how we compare things to each other. So the difference between them is that in this one, that's a population standard deviation. And in this one, that's a sample standard deviation. Yep, the T is, yep, so this is a test statistic. This is a test statistic. So the fact that it's called T makes sense because it's for doing a test. But Z just is like from German for number. Yes?
Come across a question.
Well,
And it's just, is it related to this? And so it's just final probability that like the mean one is greater than mean two. So we give like number one a mean that's like two.
that is worth talking about. So I'm just going to repeat that. You've come across some questions, they feel similar to this, and they say, what's the probability that mean one is more than mean two? Okay, I'm going to come back to that in just a moment. If I forget, then please remind me when I get to the end of this bit, because that's really important to talk about, and it is very close to being hypothesis testing, but it's not quite at the hypothesis testing bit yet. And I just want to finish this thought first. So in this one, the distribution of the test statistic is the normal distribution, like the standard normal distribution, Z. And you compare this number that you calculate to the Z number. So just as an example, you know, 30 tubs had the volume measured. And the mean was 1.2, 1.05, damn it, 1.05 litres. Standard deviation from past experience is 0.1 litres. Okay, so this is enough information to do our test. And we can say is the mean more than 1 litre. So for a person with a factory that makes ice cream, you wouldn't want to overfill them too often. But I mean, they're probably more important to not underfill them, but whatever. I've said it now. And you've just got to read the sentence very carefully and decide whether the question is more than, less than, or both of them are possible. And so this would be, the Z would be the sample mean. Damn it, I should do the whole thing properly. The null hypothesis is that the true mean is 1 litre. And I know that it's about whether it's more than 1 litre, but that's the alternative. That's more than. Because we're going to have to calculate a probability, which means we're going to have a distribution, and you can't have a distribution without picking the mean. So that's why the null is always equals, and the alternative is the one that's got the greater than or the less than. Because you have to pick a mean in order to calculate the probability. And so my Z statistic, which is the sample mean minus the mean from the hypothesis. So this mu is the mu from the hypothesis. That's really important to know that that's where that's from. And so I get 1.05 minus 1, and the sigma was 0.1, and the sample size was 30. And then I asked my calculator, and I did not bring my calculator, so I will have to use the one on my phone. I'm just going to stick an extra bracket in just in case, just to make sure that it really knows that all of that's there. And I get 2.73. 8. No, let's round it off correctly. 2.739. I don't know what the numbers in the table look like. So I'm just going to have to look them up. But I think they only have 2 decimal places. Let me just check. No, that one. No, I've only got 2 decimal places, so I don't need to round off to 3 decimal places. That's waste of time.
So that would be where my sample mean fits on a Z table against my predicted.
Correct. I'm just going to say that again. That tells you where your sample mean fits on the Z table relative to the predicted mean. So the hypothesis mean, if that's what we got, the Z would have come out to 0. So if my sample mean had been 1, then when I did this calculation, I would have gotten 1 minus 1 divided by whatever. And so that would come out to 0. And mine's way out here at 2.74. Just a second. That is on the wrong screen again. I should just share the whole screen. Let's do that. Right. So 2.74 is way out here. Actually, it's probably much further out than even that, because the place where it sort of stops curving downwards and starts curving upwards is 1. So it's like all the way out here, 2.74. But nobody really cares if you've drawn it accurately. Yep.
What's the null?
In what scenario is the null hypothesis if the mu equals 0? Yep. That would be if the thing you're doing the average of is the change, usually. So you could say, like for every individual person, we asked they watched advertisement number 1 and they gave it a score out of 5. And they watched advertisement number 2 and they gave it a score out of 5. And then what we did is we did the new one, the second one minus the first one, to see how far apart the scores are. And so some people would have made the second ad score it higher, and so they'd get a positive number. Some of them would score the second ad lower, and that would be a negative number. when you did the difference. And so the question of do the people prefer these ads differently would be the same. People preferring the two ads the same would mean that the average difference is 0. That would be when you put a 0 in that spot. I made one up that worked. But in general, if the thing that you're writing down about each individual subject in the study, in your experiment, is the difference from one time to the next, then 0 is usually your hypothesis. Does that help? So mine is here, and sample means even higher would produce numbers even higher, and sample means closer to 1 would produce numbers closer to 0, and sample means lower than 1 would produce numbers on this side. Okay. So if I'm interested in whether my true mean is more than 1 or not, then sample means that came out less than 1, would not be supportive of that alternative hypothesis. So I'm only interested in this top end because it was a one-sided hypothesis. So if my hypothesis is about being more than 1, then I'm interested in the more than 0 side. Yeah. And so I would go and look up what this probability was. But my Z table doesn't tell me that probability. It tells me this probability. So in the Z table, probability that Z is less than 2.74 is there's 2.7, it goes 0, 1, 2, 3, 4. So there's 2.7, 0, 1, 2, 3, 4, 9, 9, 6, 9. Because the Z table only gives you the left-hand side, and so the probability of being more than it must be 1 minus that, which is going to be small. Uh, 0, 0, 3, 2, 0, 0, 2, no, 0, 0, 3, 1, I think. Which is really small. And so I conclude that this is strong evidence to suggest that the mean, it really is more than 1. So I reject. And concludes that the mean is more than 1. Sorry, that's a 4. So I need this probability.
Why?
That is the p-value.
Right.
So the p-value. So the p-value is the probability of being further away from the center than my test statistic. In the direction that the one-sided or two-sidedness tells me. So, and so what I want is the probability of being further than this, which is what the greater than is here. But my Z table only gives me less than. Yeah, which is sad. Sadness. If it was a lower tailed test, then the Z table would tell me the answer I want because it always gives me the left-hand side. Yeah, so the reasoning is that I want to know this information of being further out, which is why I colored it in my diagram. I want that area. And so that's the area I want, but my Z table refuses to tell me that. So I have to go 1 minus the bit in the Z table. There is an alternative way of dealing with this, is to say, and so this is a really small number, and so we reject, but there's a cutoff for when you reject, for how small that number gets. So the more like this number is really unlikely, and this tells me I'm deeply surprised that if the, I'm just going, whoa. in the universe where the true mean of the volume is 1 liter, the chances of getting a sample mean of 1.05 liters or more is this. So I am deeply surprised. If the mean really was 1, I am deeply surprised that I got a mean of 1.05, because that gave me a Z statistic of 2.74, and that's a really surprising Z statistic because this p-value is so low. And so the lower this is, the more surprised I am, and therefore the less I believe the null hypothesis. And there's a cutoff for your level of surprise, and most people pick 0.05, because Fisher, when he invented hypothesis testing 100 years ago, used 0.05 because it was a convenient spot to pick. Because 0.05 would go with the Z being nearly 2. And he thought two is a number people could remember. So that's why he picked it. So most people pick that number to be 0.05, and they call that the significance level. Is that what they call it in this course? Yeah. So this is lower than 0.05, but if someone even told me 0.01, also lower than 0.01, it's lower than most significance levels people could pick. So since it's small, I reject. But another way of dealing with this is to not calculate the p-value and to just look at what the cutoff for exactly your significance level is. So if you had a significance level of 0.05, then you could go and find the Z statistic that would have given you exactly 0.05 and compare your Z statistic to that. So I'm just going to do an alternative here. Or if the significance level is 0.05 or 5%, if you like, then the Z, this is called the critical Z. And you can go look that up in the table and go and find the one that would have exactly 0.05 above it, which is the same as having 0.95 below it. Or look it up in the T table, because the T table has a row for Z. It's my favorite way of doing it. So I'm going to go and find the T table. Must be here somewhere. So this is the row for Z here, the infinity row. And of course, it's a bit fuzzy. No, I can't read that. Have you got the original there? Ah, yeah. I think it's that one. But that just could just as easily be zeros, and it wouldn't tell me anything. I think it's that one, 0.050. So it's 1.645 is the point at which I would have 0.05 above it. So when you read this T table, when it says T 0.050, that means that there's 0.05 above it, which is the opposite way around to how the Z table works. So it would have been 1.645. And I'm just going to say that's in the, that's in the infinity row of the T table in column T 0.050, like that. That's how I got that number. And my Z, the sample Z was 2.74, which is way, way further out than that. And so I'm going to reject, because the p-value is going to be way lower than 0.05. That's the idea. So the further out that Z gets, the more surprised I am, and my Z is way further out, and so I'm way surprised. So I reject. Since sample Z is more than the critical Z. So that's the other way to do it. How are we feeling about that process? If nothing else, this proves that I know about this process, and you can come and talk to me in person if you want to talk more. Yeah. So a lot of the decisions here are like, well, there's this full process and we can get all the way to a p-value, but technically I don't really need to know the p-value if I've got a significance level. I just need to know if it's less than the significance level, which what that means, I just need to know that the z is further out than the z that would have given me 0.05. So yeah, that's one of the reasons I give you some practice at doing these probabilities before they get to this point. But I would have loved them to have some exercises that just said, you know, the probability of z being greater than 2.74, is it more or less than 0.05? Yep.
I was going to ask you, find the probability like we said like no will be like an improvement or like improvement or not. But can you also find if you've got like a mean and you get your significance level, say it's like that, and you've got 5% significance, you find a probability that it will become something like just using the same thing.
Yeah, you can. And that's, but I'm promising to get there. But yes, you can. I'm just going to check if I understand the question. You're saying that what if, nope, I don't understand the question.
So if you've got sort of like your
yeah,
and you've got your one. Yeah, you're 95% significant level, and you can work, you just work out probability that it equals something other than,
yeah, other than the critical one, other than this one or the other critical ones, you can figure out the probabilities anywhere. Yes, you can. And that is something that is in this course. And so I will do it. I'm almost ready to do the T. I'm going to go to the T test. So the T test will work similarly. And the difference will be, I'm going to do the same story. "30 tubs had the volume measured and mean was 1.05 litres. The standard deviation from the sample was 0.1 litres. So now the only thing I've changed is where this standard deviation came from. This standard deviation was from past experience. This standard deviation is from my current sample. That's the only thing I've changed. And that makes a difference. It turns this situation into this situation. So you have to read your question very carefully to say, where did that standard deviation come from? Did they say, you can assume the standard deviation of the population is this, or from the, before they changed the production, the factories, the filling machine, it was this standard deviation, we'll assume it's the same. But if they say the sample standard deviation was this, and that's the only standard deviation they give you, then you must use a T. And so it will still be the same, but we'll do the whole same story. Is the mean more than 1 litre? So we've got the null hypothesis, mu is 1 litre. The alternative hypotenuse, mu is greater than 1 litre. Officially, you should say down, let mu be the true mean. It's supposed to tell me what the mu stands for. And then the T is going to be x bar minus mu on S on root N, because sigma is what you use for the population standard deviation, and S is what you use for the sample standard deviation. Because sigma makes that sound in Greek, so it's the matching thing for this. In the same way as mu makes that sound in Greek, and it's for mean. That's why we use it. But weirdly, we don't use little m for the sample mean. You can do it. Come on. There we go. And the calculation will be exactly the same. And the graph will look similar, And I can't tell from my bad drawing if it's any different. But the point is that this curve is in fact not quite the same as this curve, because this is a T and this is a Z. And this is the T that goes with a sample size of 30. So what we actually have is that the distribution is the T with 29 degrees of freedom. In this situation, it's one less than the sample size. And I think there's a reason why. I think it is that we're imagining all of the other data sets that would have had the same sample mean. That's what we're imagining. Or possibly the same population mean. That's better. And since we've kept the mean the same, you can change all but one of the data values and not change the mean by adjusting the last one. So that's the idea. So I could choose 29 new data values, but if I wanted to keep the mean the same, I'd have to figure out what the 30th one was to keep it the same. But whatever, it's just -1 in this situation. And so I would have to go and look in the T table in row 29, but I don't think it has a row 29, but I'll just check. There's row 28. Oh, there is a row 29. Yay. Okay, so row 29. Now, here's the thing. I can't figure out the exact p-value because it doesn't tell me. There's 2.7. I'm just going to put back here. This is the p-value here, that area. I can't figure that out. I can't figure out what it is so that I can compare it to 0.05 because my 2.74 isn't on my table. 2.74 is between these two. So my 2.74 is not on the table, so I can't figure out the p-value. But I can know that it's between whatever this number is and whatever this number is. But my that's 0.010 and 0.005. So in the table, the T table, row 29, the T for 0.00 for 0.01 was 2.462, and the T for 0.005 was 2.756. Damn it. That's what the table said, and so I've written them down. And my, so they're there, and so the sample T was 2.74. And so that means that the p-value is between here and here. My table doesn't have the number I want, but it does have numbers nearby. So if it had been 2.462, that'd be here. That area would have been 0.01. And if it was 2.756, that area would have been 0.005. So the real one is somewhere between, probably closer to 0.005 than 0.01. Yeah, so you can say that the p-value is between 0.005 and 0.001. If someone asked you, what is the p-value? That's the best answer you could give, that it's between these two numbers. But you definitely know it's less than 0.05, and so you could reject it at the 0.05 level. You can reject at the not 0.001. You can reject at the 0.01 level as well, because it's definitely less than 0.01 because it's between here and here. So but if someone told you the 0.01 level to begin with, you wouldn't need to know both numbers nearby. You'd only need to know this one. And you go, well, it's further out than that, and so I reject. Yeah. So I don't know, some lecturers say, give a range for the p-value when they ask a question like this, and then you won't give an answer like this. But some of them say, do you reject or retain? And they don't ask for a p-value, and then you can just compare it to the critical value. Yeah. But I will say to you something important here. the p-value for the z was 0.003, which is lower than 0.005, whereas the p-value for t was more than 0.005. So the p-value for the t is just a little higher than the p-value for the z. And that's what Gossett invented, this system where he's saying, look, I haven't got the real standard deviation, so I'm going to have something that's a little more conservative and doesn't reject quite as often because I don't have quite as much information if I have to do the sample size, sorry, the sample standard deviation. Just for completeness' sake, I will put it here and say, or the significance level is 0.05, then the critical T from row 29 and 0.05 is 1.699. And the sample T was 2.74, so reject. Since the sample T was more than the critical T. So it works the same way. It's just that the actual number was different because you had to look it up in the T table instead of the Z table. Now, your lecturer is probably interested in you knowing how to do both of these things, how to both calculate a p-value directly and compare to a critical value. So it's very likely that there will be a question in the exam that will get you to do one and a different question that will get you to do the other. Because they taught you both, and so they must be interested in knowing you that you can do both. But I can't be sure. That's just my instinct based on what I know about how lecturers think. So, yeah. Okay. I will answer your question now. They go all the way back to your question. I promised I would, and I will. So, I'm going to do an interlude here. Sampling distributions. So all of this is based on the concept of sampling distributions, and sampling distributions are based on the idea that anything that you could calculate or write down from ever has a probability distribution to describe all of the things it could be and how likely they all are. So everything has a distribution. So if you said, cool, I'm going to collect 20 of these people and they've got a mean of this and a standard deviation of this, and 30 of these people and they've got a mean of this and a standard deviation of this. And then I'm going to subtract those two means. And that's a process that you can do over and over technically. And you can imagine all of the differences of means that could have happened, and they will have a distribution. And the reason that you would want to know that distribution is to know how likely it is to get a certain answer. Okay. The second thing is, though, that distributions are related to each other. Okay, so here's my example. Wait, take me a moment. I'm thinking of a context. It's the hardest bit of stats. Foreign cats have weights on average 6 kilograms. And deviation. This is not a very business related one, but I don't care. Well, with standard deviation, like 0.1 kilograms, let's go 0.2. And tabby cats, that are on average 5.5 kilograms. With standard deviation 0.3 kilograms. Okay, so 20 orange cats. Have their weight measured, and 25 tabby cats have their weight measured. What is the probability that the mean for orange cats is lower than the mean for tabby cats? There you go. That's my question. That's the kind of question you're thinking of, right? Well, not cats probably, but you know, the vibe is right. Okay. So just based on the story they've told, that should be a low probability because on average, orange cats are heavier than tabby cats. This is in fact the truth. It's definitely true for my two cats. In case you're wanting to know, my orange cat's name is Oliver and my tabby cat's name is Tabitha. Okay. So if someone asks you a probability, the only way to know any probability is to know all of the things that could have happened and how likely they all are. And then you compare the situation you've got to all of those things. Like for when you roll a single die, the only reason you know that the probability of getting a 5 is 1 in 6 is because you compared that to all the other things that could have happened. And so that's what we need to know. So we need to know a distribution. So the first thing that occurs to me when someone asks me a question with what's the probability is to say, what's the distribution? They didn't tell me that they were normally distributed, but I'm going to assume that they are because I don't have another way of doing it. And probably if someone gave me this as an exam question, they would have said normally distributed or something. But I'm going to assume normal distribution. Okay, so what that means is I've got my orange cats. I shall call it XO is the orange cats. The XO is normal with mean, what was it, 6? And standard deviation 0.2. And XT is the weight. And so XT is normal with mean 5.5 and standard deviation 0.3. Cool. So that's the information they've told me right from the start. They're the two original distributions. And then they've actually got 20 orange cats and calculated the average of those weights. And so I will say this. And when you do so this is the thing, just be careful. There's lots of different cats here. If I calculate the weights of all of those, of a group of 20 of them and average them, then there's lots of different averages that could have happened if I had chosen lots of different collections of cats. So there's still a distribution. There's still different options for what the mean could have been. The true mean is 6, but a group of 20 cats might not have a mean of 6 because you might accidentally choose some that are all heavier than the mean. So just wanted to say that aloud is really important. So this is also normally distributed, and the mean of the sample means will still be 6, but the sample standard deviation will be this. So individual cats are more spread out than the collection of means from groups of 20 cats. And this is a sampling distribution thing. And that's why when you do the t-test, there's a sigma on root n thing. That's why it's there, because of this sample mean thing. And so x bar t is the weight, the mean weight x bar t is normal with mu is 5.5 and sigma is 0.3 on root 25. Okay, we're doing well. It's the only way I know how to do it without losing track of everything that's going on. And so now I want to pick one of these means and one of these means and subtract them. Because that's how to tell whether something is higher or lower than another thing, right? Maybe I should subtract them the other way. Whatever, I'm here now. And this is also a normal distribution, D for difference, by the way. If you subtract two normal distributions, you get a new normal distribution. And as long as you assume that these two are independent, which I'm pretty sure they are, they're different breeds of cats. Here's the difference. Difference in the mean weights. So D is also normal with mean the difference in the means. And standard deviation, this is the tricky bit. Okay. So standard deviations add in a Pythagoras' theorem sort of way. You remember Pythagoras' theorem with the a squared plus the b squared? Yep. So standard deviations add in a Pythagoras' theorem sort of way. And so this will be the square root of the two standard deviations squared. Yep. That is how it's done. You don't subtract them because the subtracting bit got squared, because technically it's a minus here because of this minus is actually inside that bracket, technically, just so you know. And that is whatever the hell it is. Like, we can calculate that thing. I mean, if we wanted to do some maths on it, it would be 0.2 squared on 20 plus 0.3 squared on 25. But, you know, there's a number for that. So now I have the distribution of this final single thing. And now I can actually look at what the original question was, which is I want the probability that the mean for orange cats is less than the mean for tabby cats. That's the maths version of this statement. So the probability of, that's what this bit is. And the mean for orange cats, that's this bit. And lower than is this bit. And mean for tabby cats, that's this bit. This is literally a math symbols version of that sentence. And that's the same as that. I'm going to subtract xt from both parts and get this. And that's the same as my d is less than 0. And that I can do because I have a normal distribution with mean 0.5 and standard deviation, whatever the hell this is. I shall call that number. And I am interested in the probability of being, whoa, that's not where 0 is. So 0 is over here somewhere, right? And I want this probability. Because I want D to be less than 0. The mean is 0.5, so 0 is over here. Cool. So if I had a machine that could do normal distributions without converting to Z, then I would look that up. So Excel, for example, can calculate this directly if you just tell it the mean and the standard deviation. But since you're in an exam and you don't have a machine that can do that, you would have to convert this to a Z by subtracting the mean and dividing by the standard deviation. So I would have to go, that's the probability that Z is less than minus the mean and divide by the standard deviation. Well, whatever that number worked out to be that we had earlier. And that's what calculators are for, Max. So I have the square root of 0.2 squared divided by 20 plus 0.3 squared divided by 25. And then I have minus 0.5 divided by that answer, minus 6.68. All right, so that's like basically 0. So I would go and look up this number in the Z table, but my Z table only goes down to minus 3. Let me just prove that to you. That's the T table. The Z table only goes down to minus 3.09. So that's pretty much just nothing. So my diagram was not at all accurate before. My diagram was actually should have been like, this is my Z, like way down here. That's my minus 6.68. So that is approximately 0. Cool. Damn it. I just want to do a what if. What if the sigma for my orange cats had been 0.8 and the sigma for my tabby cats had been 0.9? Just want to see what would have happened. And then that would have, do some working, and I would have gotten my D would have had my sigma of and that would have come out to 0.25377. And so my Z would have come out to, in this case, I would have gotten the probability that Z is less than oh, crap. I got it wrong before. It's not divided by that. It's divided. No, that's right. So good. I did not get it wrong. The world is okay. And so that is Z is less than minus 1.97. That would have worked out to that number. And then when I looked up my Z table and went over to minus 1.97, so there's minus 1.9 there, 0, 1, 2, 3, 4, 5, 6, 7.0244. And the table gives me the less than anyway, so I don't have to do any one minusing stuff. So I just want to do a what if to show you that it can come out to not 0, so you can see how that works. And if they had asked what's the probability that my orange cat is more than my tabby cat, well, that would be 1 minus this, because that's the opposite way around. Yeah. How do you feel about that? Right. Yeah. Okay. Yeah. So for me, the important bit is this bit where I just slowly work my way through all the normal distributions involved so that I get to this point. You can theoretically do this in one go and go straight to here, but I can't think that way. Yeah. So, but this here, now that I've got it, this is the calculation that's involved when you do the two-sample t-test, where you're comparing two means. So that's my interlude, and I'm going to go back to the two-sample t-test now, but I just want to label all my pages. These notes will go on the Maths Learning Centre website afterwards, so you can get them from me. They won't be in my uni because I don't have access to your my uni, but I will put them on the Maths Learning Centre website, and I'll send you all an email when it's ready, but it won't be ready till tomorrow. So I have to feed my daughter school tonight, so it's not going to happen for them. Yeah. So interlude over. The last hypothesis test we have is my Z/T test for two means. And they work based on that calculation that I just did. That whole thing with the square roots and stuff, that appears in the Z/T test for two means. And there are actually 3 of these. 2 of them are t-tests and 1 of them is a z-test. And I'm not going to do the whole thing split sideways like I did last time, because that was a bad choice. But I do want to put them all together here. So there's a z-test, there's a pooled t-test, and there's an unpooled t-test. So the z-test happens when you know the true standard deviations. Just the story for this is you have 2 different situations, and they both have means and standard deviations of their own. That's the story that we're in. And the question is, are these 2 means equal, or is one more or less than the other? So in that story just then, it was I've got 2 breeds of cat, and I'm interested in whether their weights are different. So there's 2 standard deviations involved here. In the pooled t-test, we don't know what the true standard deviations are, but we assume that they are the same. And in the unpooled t-test, we don't know the true standard deviations, but we don't assume they're the same. They are the 3 situations. And all of them have the same shape for how the calculation is done. They will all look like this. They'll be like Z is the mean from one group minus the mean from the other group divided by something with under a square root. And this one will be the mean for one group minus the mean for the other group divided by something under a square root. And so will this one. But what's under the square root will be different for each of them. So for this one, this thing under the square root, it'll be sigma 1 squared on n1 plus sigma 2 squared on n2, where n1 is the sample size for group situation 1, and n2 is the sample size for group 2 or situation 2. And these are the 2 different standard deviations. And over here, it looks exactly the same, except instead of S's, sigmas, they're S's. Okay? It's this middle one that's the dodgy one. but it's okay. The thing that, this is not how your lecturer will write it, but I want to write it this way for a good reason, because it's easier to see how they're the same and how they're different. There's still an N1 and an N2, that bit's the same. So this bit's all the same. But what we have is this new pooled standard deviation on both of them. And you can, if you want, factorize this out to get this, if you want. But I find it easier to process this one because they're all the same shape. And the difference is that you have to then figure out what is this SP? Bear with me. SP squared, so you have to square root it to figure out what SP is. So someone can confirm that I've got this right, but it's good for me to try and practice remembering it, and you should do the same. And write, do you get a sheet of notes? Yeah, write it on there. SP is, bear with me. So just let me say what SP is for. The idea is that if you assume that the true standard deviation is the same, is equal, then theoretically you could calculate one big standard deviation from the big group that's the two cats joined together. And so I'm almost certain it is this, and you can check if I'm right. Okay, it should be N1 minus 1 times S1 squared plus N2 minus 1 times S2 squared over N1 plus N2 minus 2. Eee. Okay. So, yay. When you calculate a standard deviation, you have to add up the squares of how far everything is from the mean, and then divide by the sample size minus 1. So if you times it by the sample size minus 1, then it's how far everything is from the mean added up. And so this is how far everything in group 1 is from the mean squared. This is how far everything is in group 2 is from their mean squared. And so this is the total of how far everything is from their group mean squared. And then you divide by this because reasons. Yeah. And this N1 plus N2 minus 2, that is N1 minus 1 plus N2 minus 1. Like, this is what the formula says, but it's worth noting that's N1 minus 1 plus N2 minus 1. I kind of like thinking about it that way. So you're literally just adding those two things together. And so this pooled standard deviation is kind of an idea of saying, well, can I get from both of them this kind of combined standard deviation somehow? And so this is the most complicated one. These two look identical. It just depends on where the information of where the standard deviation came from. Yeah, and this one looks the same as these as well. It's just that you have to first calculate what this SP is. And the rule for deciding whether you should use this one is usually that the biggest standard deviation is not more than twice the other one. But I don't know if your lecturer gave you that, did they? Anyway, that's what I was always taught. So if one of the standard deviations was 3 and the other one was 5, then you'd use this one, because you only have to use the unpooled one if one standard deviation is more than twice the other one. So, yeah. So this would happen when S1 is less than 2 times, S2 is less than 2 times S1, or whichever way, it doesn't matter right way around it is, but the bigger one is less than twice the other one. Anyway, but everything else is the same. And I will say in this one, the degrees of freedom is N1 plus N2 minus 2. And in this one, the degrees of freedom is wickedly horrible formula, but most people use whichever is the smallest of N1 and minus 1 and N2 minus 1. Yeah. Is that what a lecturer told to do? No, that's okay. There is a horrible formula for what the degrees of freedom, is that what they said? Yeah. There is a horrible formula for what the degrees of freedom actually is, but it's horrible. No one remembers it. No one even shows you it. And most computers just do it on its own when you ask it to do a t-test. So if you do econometrics next year, you'll get a computer to do this for you. But I don't know what the course will look like next year. University of Adelaide, they're currently using a computer program called Stata to do it. But who knows next year, because I don't know what they do at UniSA. So you'll get the new combined version if you do econometrics in the future. Yeah, so econometrics should have been called data analytics 2, but econometrics sounds fancier, I guess. To be fair, this course used to be called just Economics Statistics 1. But data analytics sounds cooler, so anyway. But all of them happen in the same situation where you've got two stories, two situations, two groups, and they both have calculations of a mean, and you're trying to see if the means are different. Yeah, but you have to read the story carefully to decide whether the question is, are the means the same, or are the means, is one mean more than the other? Does one mean less than the other? It's much more common for people to do this one as a two-tailed test. Because the question is usually, has the change in situation made a difference to the mean? And that's a two-tailed one. But if it has the change in situation increased the mean, then that's one-tailed. I should write that down. Two-tailed. That's one-tailed. Yeah. And actually, it makes no difference with this. You can do x2 minus x1 if you prefer. And that's the best one for testing whether it's increased, because then you can use the right-hand tail. So, yeah. Actually, yes. From now on, forevermore, I'm going to do x2 minus x1. So that makes more sense. Yeah, I'm going to have to stop. Sorry, because I've got another session starting in 10 minutes and I need to go to the toilet. But before I do leave properly, thoughts, questions? Yep. Yes, you can, but I make no promises of getting back to you within like a day. It might take a couple of days. The quickest way of getting information out of me is to turn up at the Maths Learning Centre. I won't be there on Monday and Tuesday mornings because I'll be in revision seminars, but the other staff, at least one of them, will know how to deal with it. But yes, you can email me. Just use the email that I emailed you from and it should work. Cool. All right.